All right, looking at example 10. So let's write the equations of polynomial function whose roots are 5, m1, negative 1, m2, and 2, m3 only. So those are the only ones, and they pass through the particular points. Okay, so for a problem like this, we're going to want to first create what's called a general equation. A general equation. Okay, and it's going to be of the form f of x equals a times x minus little a to the nth power, x minus b to the nth power, times dot 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 all the way down to whatever. Okay. Now the reason that we're going to write the general equation first is because to force it through a point, we're going to have limited options. Let's say we have a function that looks like this, and let's say it bounces and then it goes up like that. If I want to force this function through another point, like let's say this point right here, but I can't change the x-intercepts, it has to cross and bounce there. The only way to do that is to vertically stretch it. Okay, vertically stretch it to make that happen. Or let's say I want it to pass through this point down here. Okay, well, I'm going to have to reflect that now. It's going to have to cross like this. Oops, I can't have it do there. Let's say that was on an x-intercept. Let's say I want it to be this point right here. It's going to cross, and then it's going to bounce, and then it's going to go up like that. So how do we vertically stretch or reflect something across the x-axis in order to make it pass through a point? We look at our value of a. This a right here is not only the leading coefficient when you expand it out, but it's also your vertical dilation factor. Vertical dilation factor. Okay, so this is called the general equation. So let's go ahead and do that here. Based upon the roots that we have, we know our function is f of x equals 5 is the root, so x minus 5 is the corresponding factor. It's multiplicity 1, so the exponent is 1. Negative 1 is the root, so x minus negative 1, or x plus 1 is the corresponding factor. It's m2, so the factor is squared. 2 is the root, so x minus 2 is the factor, and it's m3, so that's cubed. Okay. Now, notice I didn't write an a in the front. That was my mistake. I need to move this over, and I need to put an a in the front. In fact, when you write your general equation, that should be your first step. Give it a name, f of x equals, or h of x equals, g of x equals, and put an a right away. Okay. Now we're going to do part A. I want it to pass through the point 0, 10, so I'm going to say at the point 0, 10, colon. And now I'm going to do is I'm just going to plug this in for x. I'm going to plug 10 in for f of x. So we get 10 equals a times, and when I plug in the 0 for x, I get negative 5 to the first, I get 1 squared, and I get negative 2 cubed, which is negative 8. Okay, so I literally plugged in a 0 for those three x's. And now we solve for a. We're going to get 40a, and I divide through, and I get a equals 10/40, which is 1/4. Now that you find 1/4, you transition, you say so, or therefore, or consequently, and all you got to do is plug this a back into right there into your general form. So we get f of x equals 1/4 times x minus 5 times x plus 1 squared times x minus 2 cubed. Now, if you want to sketch that graph, here's what it looks like. You got a root of 5. Here's 5. Here's 2. And here's negative 1. And you know the degree is 6 because that's the sum of the multiplicities, 3, 4, 5, 6. And the leading coefficient we found was 1/4. So it's going to come in the top and go out the top. So it bounces right here at negative 1. And it's going to wiggle at 2. So it approaches like it bounces, but then it goes down. And then it turns around and crosses at 5. So make sure when you do your M3s, you look like that. You physically approach like you're going to bounce, like it's going to go up, but then it doesn't. It goes the other way. You turn it back down, or it's bouncing from the bottom. It approaches like it's bouncing from the top, bouncing from the bottom. But anyway, this one is very reasonable. We have a y-intercept right there of 0, 10. Okay, and that's a reasonable answer because we have it crossing in positive land. All right, let's see what part B would do. Part B says now to force it through the point 1 comma negative 4. Well, here's 1 right here. If I want to force it through negative 4, I'm going to have to take those positive y values and make them negative. So I know for part B, at least for part B, if I'm going to pass it through the point 1, negative 4, I know that my a value is going to be some negative number. That's the only way to get the capacitors to reflect it. But anyway, I take the same general form, which is up here, and now I plug in a 1 for x instead of a 0, and I plug in a negative 4 for f of x. So here we go. We say at negative 1, 4, colon, we get negative 4 equals a times 1 minus 5 is negative 4. 1 plus 1 is 2. 2 squared is 4. 1 minus 2 is negative 1, and negative 1 cubed is negative 1. So here we get negative 4 equals, it looks like 16a. And if I divide through, I get negative 4/16, which is negative 1/4. So, and now what do? I plug that a back into the general form, and I get f of x is equal to negative 1/4 times x minus 5 times x plus 1 squared times x minus 2 cubed. Okay, so we have two different functions, each from the general form, and the only difference is one of them is dilated differently. This one here, for what it's worth, would come in, it would bounce here, it would pass through this point, and then it would approach like it's going to bounce, and then it would continue on the other side, and then it would turn around and do this. Okay, so let's call this one g of x. We'll give it a different name instead of f. Come back here, just so we can distinguish them. So the second one we'll call g of x, and the first one we'll still call f of x. So they exhibit the exact same behavior on the x-axis. It's a bounce, a wiggle, and a cross. A bounce, a wiggle, and a cross. One is flexed vertically to pass through the point 0, 10. The other one's reflected and dilated to pass through the point 1, negative 4. Okay, cool. That takes care of example 10. Example 11, it says find the equation of degree 2. That means it's a quadratic right away. We know it's a quadratic. If I can spell it, quadratic. With the following properties: f of negative 3 equals f of 4 equals 0, and f of 1 equals 5. Okay, so first of all, we got to decipher what information we're given. If you plug in a negative 3 and get out a 0, that means it's the point negative 3, 0. And if you plug in a 4 and get out a 0, you're going to get the point 4, 0. That means that the zeros, or the roots, are going to be x equals negative 3 and x equals 4. And we know that they're both m1s because there's two distinct roots and it's a quadratic. So there can only be two roots. So they both have to be singles. If this was degree 4 or something, we would have to know if one of them was degree 3 and the other one was degree 1, or they were both 2s or whatever. But in this case, they're both singles. It's quadratic. So this point here, 1, 5, is what I'm going to use to find my a value. This is what I use down here to write the general equation. And this is what I use to write what's called the particular equation. All right, so let's write the general equation first. Step 1, let's say f of x equals a, and if minus 3 is the root, x plus 3 is the factor to the first power, and if 4 is the root, x minus 4 is the factor to the first power. So there's your general equation. Now we're going to say for the particular equation, we're going to say at the point 1 comma 5 colon, and we set it equal to 5, and we plug in a 1 for x. So we get a times 1 plus 3 is 4. 1 minus 4 is negative 3. So we get 5 equals negative 12a. And you divide through by negative 12, and you get negative 5 twelfths. So this one does also reflect. So this one parabola opens down. So f of x must equal, we plug that right back in here to the general equation, negative 5 twelfths, x plus 3, x minus 4. It doesn't say to sketch it, but we can certainly sketch it. Here's negative 3. Here's 4. They're both single roots, and it opens downward. So it looks something like that. And if you wanted to even find the x-coordinate of the vertex, you could just average those two. 4 plus 3 is 1. 1 divided by 2 is 1/2. It's a nice little property of parabolas that the axis of symmetry is halfway between the x-intercepts. So you can just find their average, find the midpoint of the two. Okay, let's look at this one here. Example 12. Find the general equation in factored form of the following. Okay, what do I notice about this? I notice that it's an even degree polynomial just by looking at it because it has the same end behavior. I know that. It's called f. That's its name, f. It looks like it has a bounce. This looks like a wiggle. This looks like a cross. This looks like a cross. It looks like a cross. So I put 0 there. Sorry, I meant to write the multiplicities. Let's write the multiplicity. This is going to be an M2 bounce. This is an M3 wiggle. This is an M1 cross. This is an M1 cross. M1 cross. So if you add all those up, 2 plus 3 is 5, plus 1 is 6, 7, 8. This is actually a degree 8. It's degree 8. It has a positive leading coefficient because it exits on the right-hand side at the top. So let's go ahead and write it the general form. The general equation would be f of x equals a times, if negative 5 is the root, x plus 5 is the factor. Let me move this down a little bit. X plus 5 is the factor, and it's a bounce, so it's squared. The next one looks like the root is negative 2, so x plus 2 is the corresponding factor. It's a wiggle, right? It looks like it's part of a smile to part of a frown, so that's an M3. It's a triple. And then we have x. Don't forget x, or x minus 0. It crosses through the origin, so x minus 0, or just x to the first is a factor. And then we have, it looks like it crosses at 3, so x minus 3 is a factor to the first. And then it crosses again at 6, so x minus 6 to the first is the factor. Now, if we clean this up a little bit, we usually bring the x to the front, so we'll call this ax, x plus 5 squared, x plus 2 cubed, x minus 3 to the first, and then x minus 6 to the first. And then that's my final answer for the general equation. They don't give us a specific point, not on the x-axis to pass through. So the last thing I'll do is I'll just say a is greater than 0. That's about the best I can do for a. Based on this graph, I know it opens up. The right-hand behavior is positive, so the leading coefficient is positive. But in order to find the actual value of a, you would have to have a specific point that's not on the x-axis that you can plug in. So this one just asks for the general solution. All right, example 13, you're going to have a quiz on Monday, and this is going to be what your quiz will be over. So I'll say in example 13 is quiz-like, very quiz-like. So are the others. Anything from example 10 that we've done today is quiz-like. So like 10 is also very quiz-like. Okay, but I like making you get your equation from the graph because it requires you to know what the multiplicities are. So let's go ahead and number this first. -2, -3, this is -4, there's 0, here's 3. All right, and if you want to label them, this is M1, this is another M1, this is M2, it's a bounce, this is an M3. So if we add those up, 3, 4, 5, 6, 7, this is a 7th degree polynomial. And what do I know about A? Since it exits the bottom on the right, I know A is less than 0. Now what am I talking about A? This function's name is 8, so the general equation would be the following. H of x equals A times x plus 4 to the first times x plus 2 to the first times x. I'm going to go ahead and use notability, scoot that over, and I'm going to put x squared there. It's a bounce at 0 this time, so it's x minus 0 quantity squared, or just x squared. I'll pull it to the front right away, and then I get x minus 3 to the third power. So again, if we know the root, x minus that number is the factor, and the multiplicity is the exponent. So we got a cross, a bounce, and a wiggle, and I pulled the x squared in front. So there's the general equation. Now the point 1, 2 in green is the point that allows us to find the particular equation. So I'm going to say at the point, 1 comma 2, and colon, and then we plug in a 2 for h and a 1 for x. So we get 2 equals a times 1 squared, which is 1. 1 plus 4 is 5. 1 plus 2 is 3. 1 minus 3 is -2, and -2 cubed is -8. So I get 2 equals a. This ends up being -40 times 3, -120. And I divide through by -120, and I get a equals -1 over 60. -1 over 60. So that's a vertical compression by a factor of 60. Don't be surprised if your a values are always like really, really small numbers. Because a lot of times, if you were to graph this on the calculator, you would just see like a vertical line, and then a vertical line, and then you would see like a very shallow bounce, and then another vertical line. That's all you would see on your -10 to 10 window. So these graphs are very, very steep to begin with. What we're doing is we're compressing them down vertically by quite a bit, like by a factor of 60 here, so that we can see the nice local max and mins. Okay. So anyway, here's the equation. So we know that h of x then is going to be -1/60 times x squared times x plus 4 times x plus 2 times x minus 3 cubed. And there it is. There's your final equation. So write the general equation, put an a in front, name it h of x based upon the x-intercepts and what they're doing there. You got the exponents and you got the factors. Plug in your point, show your at point colon, plug it in for the right side, plug it in for the left side, find a, and then all you got to do to write your final answer is plug a back into your general equation, and ta-da, boom, you're done. Should be an easy 100 on Monday. All right, let's summarize here. What do all polynomials have in common? Well, number one, they're so much fun. Number two, they have a domain of all real numbers. That's very important. They're smooth and continuous. They have a single y-intercept. They're only going to cross the y-axis once, but they can have multiple x-intercepts up to whatever the degree is, n. Those are also called roots. Those are called zeros. They have up to n-1 relative extrema occurring in pairs. They have exponents that are whole numbers. That was on the quiz as well yesterday. They have infinite end behaviors, so it's either positive or negative infinity. No asymptotes, no holes, no jumps, no discontinuities at all. Forget this part. 1 wiggle equals 2 relative extrema. We'll talk about that later on. But to determine the degree of the polynomial with all real roots, You add the multiplicities of the real roots, which is the same as I'll add this, adding the exponents in factored form. And then the last part talks about imaginary roots. We haven't really done that yet, so you can just scratch that out. I scratched it out with a highlighter. That almost means the opposite of scratching it out. It means highlighting it. I'll just scratch it out. That's later info. Okay, so don't worry about the one wiggle. Don't worry about that. So that's what all polynomials have in common. Now, based upon their degree, if it's an even degree polynomial, they have the same end behavior. The leading coefficient tells you what the right end behavior is. It goes out the top, which is infinity, and because it's even, it has the same end behavior, so it's top in. If the leading coefficient is negative, it tells you the right end behavior. Because it's even, it's also bottom in, as it is bottom out. An even degree polynomial will have an odd number of relative extrema, or local max or mins, up to n minus 1. Okay? There's no guarantee of a 0. If the x-axis is there, they could do all their dancing and turn around before they even touch across the x-axis. But the number of possible zeros then, it could be 0, it could be that there's none, but then it's 1, 2, 3, 4, 5, 6, whatever, up to n. They are bounded, they have a restricted range. They're not all real numbers. Sometimes we can't find what the range is unless we know calculus or have a calculator. Finally, if n is an odd degree, they have opposite end behavior. Odd, opposite, they have that same sound. Odd, opposite, odd, opposite. If the leading coefficient is positive, they go out the top. Because it's an odd degree, they come in the bottom. If the leading coefficient is negative, they go out the bottom. And then the opposite, on the left side, they come in the top. They have an even number of local max or mins, relative extrema, again up to n minus 1. So an odd degree function has an even number of turning points. You are guaranteed at least one real root. That's very important. There's no way to get from one side of infinity to the other side of infinity through a continuum without having at least one real x-intercept. So the number of possible roots is not 0, 1, 2, 3, 4, 5, 6, 7, whatever, up to n, but it can't have 0. Now the nice part here, since they do go from infinity to negative infinity or vice versa, is they're unbounded y values, which means the range is all real numbers all day long. Okay, so your worksheet for 3.1 is due Monday at 9 a.m. And we will have a quiz on Monday, like anything from example 10 through 13. So if you have any questions, email me for a hall pass before 8 a.m. on the morning of, and I'll reply and use that as your hall pass. Have a great weekend, unicorns. Unicorn pride is justified.